I've got prototype molds printing on my Kudo3D Titan 1 being controlled by Photonic3D, formerly known as Creation Workshop Host. That's going on right now, but what I really want to show you today is the process by which we take a set of models, for instance this mold here, and we get it ready to print using Photonic3D. So let's start. We've got this model, right? And I modeled this in Autodesk Inventor. You could have modeled this any number of different ways. And this is a two-part mold. There's a core and a cavity. And you export each part separately as an STL file. Now the big problem when we get into SLA printing, to resin printing, is that we need to hollow out these models, and we've got to put drain holes in them, and then there may be overhangs and things that we have to worry about once we hollow out the model. So how do I do that? Right? Well, the main reason why we want to hollow out and put drain holes in and air holes in is to reduce the surface area so that the model doesn't stick to the vat while we print, and to save some resin. Saving resin should be pretty clear. Same reason on FDM printing we use sparse infill, but the suction forces are important to think about, right? I'm going to eventually, when I print, I'm going to be printing with this end here against the build plate, and that means the model is going to be built starting with this part up here, and then layer by layer the build plate will go up and down, right? You can see lots of my other videos that show the build process. Now in the middle of the build process, right, there is this void on the inside, and besides the stickiness of the resin itself and the solid parts, you also have to worry about this whole void forming kind of like a big suction cup against the bottom of the vat. And that is going to happen if this top part here is solid. So what we need is we need an air hole so that when this part goes up during printing, there isn't going to be a suction cup effect from the void. And we're going to do that with drain holes and a vent. And I've had to model the vent into this part already. That's this slice here. And this will create an air channel out the sides, and then I'm going to put holes in here using the infill tool. That way there will be a continuous air path from the interior of the model outside across this bit here and then out. So we start with this model, and then we use this Lattice Infill tool that Autodesk has on as one of their experiments. A few weeks ago, if you've noticed, the buzz was Autodesk had this video and a set of I think there was a blog article somewhere talking about how to make prints go super fast on the Autodesk Ember. And one of the ways they make prints go super fast is to sparsely fill it, and then take advantage of this tool here to put in holes. So there's drain holes here, and if I increase the lattice opacity, you see that there's a lattice on the inside. So I use this tool here, which is web-based, in order to produce this part. Now, how does this go? So let me refresh this now, take it back to its original state, and then let's go through that process very briefly. Now after refreshing, this brings us into the default settings for Lattice Infill. Now in my case, I don't need a 3mm shell. I only want a 1mm shell, and I'm going to leave the rest set like this for now. There's this default screw part here, and I'm going to go and pick my own. I'm going to pick this diffuser mold core, load it, and then take a look at how this goes. Now, the orientation of the part really matters, because this tool only likes to make escape holes against the surface planes that are normal to the bottom. And what that means is that it's really hard. In general, I won't easily be able to make drain holes down here, a whole bunch of spots. The tool will complain about just saying, give me an error saying unable to create drain hole. You really can only easily create drain holes on the sides in the current version of the product. And so I've brought in this model flat, which is the default way that it exported. It does mean, though, that we want to plate this thing afterwards. I'm not going to print it in this orientation against the print bed, but I am going to process it. Because it's oriented this way, the infill may not be optimal for going top down, so I'm going to change the infill rotation a bit, and because I am going to be printing it upright like this. Change the infill rotation by 90 degrees, and we're just about set. The only thing I need to do now is the drain holes. Now remember, if I pull this over to the side here, you'll see that there is the cutout here, which was for my air vent. Now I want to put in 2 holes that'll align with those air vents. So I go to escape holes, I'm going to make my hole diameter 8, and then I'm going to go add hole, and this hole tool conveniently shows me the normal, and I'm going to put one here, and I'm going to put one here. Now these holes now align with, they overlap with this channel, and that'll create then this continuous air channel that goes from the inside out through the holes, and then the sides out through those channels. Now we're set. I'm going to export this now and export the mesh, and this is going to come out as an OBJ file. The OBJ file that this thing saves could have, and usually does have, non-manifold geometry in it that is going to mess up the slicer. So I did this on both of the parts, and then I came over to Cloud Netfab. This is the ever famous cloud version of Netfab. You can go cloud.netfab.com or here, which will redirect you to netfab.azure websites. This is a cloud version of Netfab that only does 3D print fixing. And you basically just come here, you go upload, and you select the part, and this thing will take OBJ files. Remember, we export an STL file, but the Autodesk tool likes exports OBJ files for whatever reason. So we're now in kind of OBJ file land, but that's no problem. I can come in to where I saved my model and pick up my OBJ file. Right, this is the infill OBJ file that I had, and then I'll upload it, and then it'll repair and download. This takes a bit of time, so I've done that already, and we now have the fixed OBJ files downloaded. Once I have the fixed OBJ files downloaded, I then need to lay them out. And you can use a number of different tools for it. Simplify3D is pretty nice. I use that. It is a paid tool, so you can also use Cura, which I'll show you here. Setting this up is relatively simple. You're going to have to add a new machine, and none of these settings matter because we're not actually going to print with this. What really matters is just setting the dimensions of the bed, the X, the Y, and the Z height, so that you know that your part will fit, and so that you can lay out the part relative to the print bed. Right? So 168 by 94 by 250. Right? And this corresponds to my current settings approximately. So I am going to load the model, and then I'm going to pick, say, my 2 fixed infills, which are in the form of OBJ files, and then I'll open those, and they'll come in. Now I'm going to have to edit these, and I'm going to have to do a couple of operations. I'm obviously going to have to rotate these in order to line them up properly, because obviously it's not going to be able to print like this. So I'll rotate this guy here 90 degrees, and I'm going to rotate this guy here 90 degrees. And that's good. The holes are at the bottom where I want them, and then I can kind of move them around and they stick to the print bed or whatever. But there's going to be an issue. And the issue here is that when I export this bed setup, my positioning isn't going to be saved, in that the model of the bed isn't going to get exported along with this. And that means that the center of this whole dimension is what's going to end up getting centered here when I take it to SLAcer, when I slice it later. When I slice it here, the slicing tools that are online that I'm going to be using don't have the ability to move the XY dimensions or select the XY location or do XY translation of these models. And so I'm not going to be able to control exactly where on the print bed this fits. It looks like I have chosen where it sits on the print bed, but in reality the center of this combined model is going to go to the center of the print bed unless I do something. And in this case, what I need to do is I need to make something that's going to frame the dimensions of this print bed so that it'll center properly. And that's what this STL bounding frame is. I modeled this very, very quickly in OnShape. It's an online tool that is free for non-commercial use. And essentially what I did was I modeled out an object that's the maximum dimensions of my print bed, which in this case is at 100 microns. It's 192 by 108 millimeters because I've got a 1920 by 1080 projector. And so I've modeled out 192 by 108, made a rectangle, and then I used the offset tool to offset it by a really, really small amount, by 0.5 millimeter. And then I extruded it, and I extruded it only by 0.01 millimeters, right? Only by 10 microns. And what I want to do here is I don't actually want this frame to print. What I want is for this frame to force the slicer to lay things out relative to this largest XY component, but I don't actually want it to print out. I just need this in order to bound the dimensions of the exported STL file and properly position the parts relative to the print bed. So this frame kind of represents the print bed. So I'm going to need to add it. I exported, whoops, right? It's relatively easy here. You go export, and then you can export this guy as an STL file. Now, since that STL frame is really, really tiny, I'm not going to be able to select it easily here. So instead, what I'm going to do is I'm going to load it first. And I'm going to set it up here, and it's going to be centered by default. You'll notice that it's actually outside of the build area, which is actually totally fine. So I've got that. Next, I'll load my other two models, my fixed OBJ files that came from NetFab. And those kind of displaced the original guy. And so let me then go and reset all object positions, and now these guys go back to kind of some default orientation. I'm not sure what they're resetting it to, but the important thing is that it jumped this back to the center. And now then I can come and do the rotations here to get this guy rotated where I want it to. So now I've got these guys rotated, laid out where I want them to. I've got the drain holes pointing down, the vents pointing down. These guys are placed in the most in focus and brightest part of my projector. Now the last thing I need to do is mirror these parts. You remember in Creation Workshop, you often need to do this like mirror x-axis, mirror y-axis if you're doing bottom up. And we need to do the mirroring also. We're not going to mirror the whole image because we can't do that. Instead, I'm going to mirror the parts individually in 3 dimensions. I'm going to mirror that guy Y, I'm going to mirror this guy Y. That actually, changes their orientation. So fine, I'll move these around so they get back into their location, right? So I can mess around with this a bit, get this into the location I want, and then I can then save the model, and this then I can save as, this will be the whole scene, which will be, it's got Y flip, it's infilled, and then I did it in Cura. So I'll go replace that. That'll save it, right? If we zoom into the model here, you can see the infill. So now we've got our scene all set up to slice. So now we are using SLAcer.js. This is a pretty cool project here that is a pretty fast web that I'm going to use to slice this scene. Right? And you'll notice that when I imported this, these two guys didn't jump to the center. They came in and were correctly aligned. Basically, I'll go to Browse, and then I will open up the scene that I have. And I can pull this up, and these guys are in the correct location. Now, there are a couple of parameters that you're going to need in order for this to slice properly. In particular, you need to set the build volume here, because this is going to set the dimensions of your build, right? Which is this inner box here. This outer line here, this is the outside of the frame kind of framing guide, right? The STL bounding box. So that's not going to get reflected. But this here, this inner box is controlled by the build volume. You need to know what this is so that the image is the correct size, and you're also going to need to get the dot pitch correct. And we've got width, height, but then you've got this mysterious parameter here, diagonal size, that we're going to have to figure out. So how do we figure out what these values are? Well, we start with Creation Workshop host, Photonic3D. What we have under controls is there is a control for doing calibration. I think that the calibration control does not show up right now because I'm in the middle of printing, but there's a calibration control that lets you set millimeters, and then you move pixels to match up. And I'll do a separate video on exactly how that works. And what that's going to give you is then the Creation Workshop host, Photonic3D, is going to figure out what the pixels per millimeter in each of the X and Y axes are for your printer. And you can use that to do all of the other calibration tasks for your printer. Now, how do I get that information? Because once I do calibration, it actually doesn't show that information in the UI, and you're going to need to get that from the REST API or from the file. So there's a file that'll be on your Raspberry Pi in root profiles where this gets saved to, and that's going to match basically whatever you have your slicing profile set to. That is where this is going to be saved. So there are going to be 3 files with exactly these names in root profiles, or you can use the REST API. We've swaggerized it. So if you take this REST API endpoint for swagger.json, and then you have a Swagger UI, the Swagger UI will then pull the documentation here, and we can then check the slicing profiles. So what we want is this machine slicing profiles list. Try it out, and then we'll get the response. The response here is, here we've got Titan 1 88 FlexVat. That's the one that I'm going to use to print. And then we'll see this dots per millimeter X and Y, 11.27, 11.32. This is what I got from empirically doing the calibration sequence. This roughly is 11.3 by 11.3. And that is going to give us both the bed dimensions and the diagonal size that I'm going to need. So how do I figure this out? Well, my printer is capable of printing the entire projectable area. And that means 1920 by 1080. So if it's 1920 pixels divided by 11.3 pixels per millimeter, that's 169.91 millimeters in X. And that's what I enter here into the X build volume. Then I'm going to do the same thing for Y. Y is 1080. So 1080 divided by 11.3, that's 95.575. So that rounds up to 95.58, and that's my Y. The Z height is the Z height based on your Z stage. That's known for my machine to be 250. I don't need to compute that out. So these are the physical dimensions of my printable area based upon the current projected size. That means my projection size is 169.91 by 95.58. I then need to also compute the diagonal size in order to get this dot pitch right. Because by default, when you first load SLAcer.js, this will be set to some random number like 22 or something. And if this number is not correct, the PNGs will not come out at the correct size. So if you slice this and you see that the PNGs don't have, are all black, or your images are off in one corner or something weird like that, you didn't set the diagonal size correct. And we're going to have to use the Pythagorean theorem here to figure this out, because we remember this diagonal size is the hypotenuse of a right triangle, right? So a squared plus b squared equals c squared. We have a and b here, right? We have the two right edges of the triangle here, and so we need to compute the square root of a squared plus b squared, right? And so we're going to need to go a squared, which is then 169 squared plus b squared, right? And so that's 38,401, and we're going to need to take the square root of this. So we're going to take the square root of this, and that's 194.9475. And that's what I need to enter here in this diagonal size here, which will be 194.95. Whoops. 194.95, right? And that gives me the dot pitch 0.09, because we're only to two significant figures. You can double check this, because the dot pitch that comes out should be 1 over the pixel density here. All right, and so if this tool let me do it, I could have entered it in manually, but this essentially, this dot pitch is millimeters per pixel, and this value here is pixels per millimeter. And so if I go here and say 1 over 11.3, this is 0.08849, which this has rounded up to 0.09 because this only has two significant figures. So this matches up. This is correct. So now that I've imported this, it's laid out in the right location. I've got the bounding box, and then when I move this up, I can then preview the slices, and I want to make sure that I don't see any really weird slices that are that contain weird triangles or things that might indicate that I have non-manifold geometry. SLAcer.js does not do geometry fixing, so if you have non-manifold geometry, really weird things are going to happen. Then we got to set our standard parameters. We set the layer height here. This is going to be the same layer height that we set for the slicing parameters. And so in my printer, I've got my slice height set to 0.1 millimeters. That's 100 microns. So I have the layer height set to 100 microns. This light on delay, light off delay, these do not matter. Because what I'm doing is I want to make a zip file. And then I also want speed mode. Speed mode means I'm just going to render the images to the zip file. It's not going to try to project them. There's another mode where you could have these projected out to a monitor, maybe if you're going to manually enter commands, probably for some future functionality, but that's not what we need. We just want to make a zip file. So we're going to do this, and then I'm going to slice. You'll see that this slice is pretty fast. Not fast enough that I'm going to force you to sit through all of this, since this is 1,460 layers, but this is pretty speedy slicing, especially since this is done right inside of your browser. I didn't need to download any software for this. Now this is done. We've sliced the whole thing. Now we need to download the zip file that contains the slices. So we'll click on this zip button, and it'll do whatever it does to compute the zip, and then we'll save it here. I'll save it with the sample name. The real one here is diffuser mode lattice infill, the original one. I'll use the scrap name here, SLAcer.zip, the default, overwrite it, and then let's see what is in here. If I open up this zip file, we've got a folder here with slices. The fact that this isn't a folder doesn't matter. The zip file, or sorry, the slice PNG processor in Photonic3D doesn't care whether or not your PNGs are in folders or not. It looks for all the PNGs that are there, that are in the zip file. And then we've got our slices here, 1 through whatever. You'll notice that these are not 0 padded, and that is okay. The zip of slices processor in Photonic3D will do the correct thing when it sees these numbers. So whether your slices are padded or not doesn't make any difference. Let's take a look at one of these slices. We've got one.png here, and you can see here that okay, I've got a slice, and then I can close that, work my way down to maybe the last one. We go to 1460, and we can see here 1460 contains the slice at the top. If I really wanted to preview through all of these, I could extract the zip file and take a look, but I do sometimes want to make edits to, in particular, layer 1. It may be that I want to manually add in some additional attachment, and I can do that. Let me go back to some random directory here. What I can do is I can grab one.png. I can open it, say, with whatever your favorite image editor. MS Paint works really well here. If you're on Windows, I'm using GIMP, which is a little bit overpowered for this purpose, because then I have to do things like select this, and then if I want to make this area a little bit bigger, I can do a delete, and then fill this, and then I might want to make this area bigger, like this, and I'll do a delete, and then I'll do a fill. I might do the same for this section down here, which is partially off screen. Delete, and then fill. There we go. And then the easiest way for me to save this then is to just go overwrite one.png. and then close this guy down. And then it's going to warn me that I didn't really save it in its native format, and so I'll go just discard changes. And if I come back here, I can actually see in the preview already that these things are already here, and then I can drag this back into the zip file, and then Roller or your built-in Windows zip file or whatever will replace the file, and then we can upload this. When we're ready to upload this, just go over to Creation Workshop host. We'll hit upload, choose file, and here's my SLAcer.zip. And then we'll let this upload in the background, and it'll be ready to print. Now, of course, we didn't set any layer settings, and you have to do all of that using the default slicing calculators here. And I'm not going to go over these today. There's some good documentation here, and hopefully if you're using a printer like a Move3D or the Titan 1 or the photocentric printer, some of the team members have created calculators for it. But you'll need to determine what the Z-lift distance, lift speed, and exposure time are. You set the exposure time for first layers, the number of first layers. This is off by 1, so 0 really means 1. And then the exposure time for the rest of the part. And then you can do all kinds of modifications to them. So you could put a function here that might linearly ramp down the exposure time from the first layers down to the exposure time over a sequence of 10, 20, 30 layers if you wanted to. Same thing, the lift speed. Here I've got an S-curve, which you can look at, which depending on the surface area of the part, I've got something overriding it. I've got this guy here overriding it. But anyway, depending on the surface area of the part, this build area millimeters, it's going to then go faster or slower. Lift distance for the stock Kudo3D Titan 1, this will also vary based upon the surface area. I'm using a homemade flex vat, which I'll make another video about. And with the homemade flex vat, I did some tests, and it seems to take about 2.5 millimeters of lift no matter what the surface area is. So it's just fixed here at 3. You're going to need the G-code that's correct for your printer, and that's pretty straightforward G-code. Just need to figure out what the correct sequences are for your printers. If they're sliders or wipers or whatever, the G-code for that will need to go in here. My printer is relatively simple mechanically. It's only got a Z stage, so this is just a lift sequence to go up, go back down, and then to asynchronously wait, or to synchronously wait until the sequence is done processing. And so once I've got this set up, got my printable in here, then all I need to do is go select it and then go print, which of course I'm not going to because I'm currently printing that object right now.